All right, let's see. Hide. All right, so good morning and happy Thursday. How's everybody doing? All right, everyone has the classes they want outside of this one. All right. Okay. So today the plan is to go over agent architecture, teach you a little bit about some of the vocab. And what I've decided to do is to save the walkthrough for the Pac-Man game for tomorrow's lab. Okay. And so please bring your computer with you. Again, this is not a game programming class. There are other departments that offer classes for that. But we will be using things from a Python-based Pac-Man game to apply various learning techniques in designing representations and methods and algorithms concerning rational agents. Okay. And so tomorrow will be sort of an early peek at project number two because it's going to take some time to walk you through the main loop and different parts of the code base. Now, certainly it's recommended that you do not spend your time going through all of the aspects of all of the code of the Pac-Man game, right? It's fairly substantial. And the point of the class is not to implement a gaming environment, is to implement learning algorithms and AI methods. Okay? All right. So why don't we get started? Before we begin, the usual administrative bits. Of course, the reading is outlined completely for the semester in the syllabus. So please make sure you're reading the syllabus. Project number one is due this coming Tuesday at 11:59 p.m. If you've had courses with me before, usually I have the deadline at 12:01 the next morning, but I've decided not to do that because there was sometimes confusion. People would just look at the date and not when the project was due as described in the PDF. So please make sure you're getting on it as soon as possible. The purpose of project number one, not that many moving parts. The purpose of it is to get you acquainted with how you submit things to the auto grader for this class. Okay. I've tested it many times, but as you can imagine, sometimes things glitch. So please make sure you're following the instructions. Of particular importance will be when you submit, you create a zip file, and that zip file should not have directories in it. All of your Python code should be at the level of the zip file, not inside of a folder, or else you'll break the autograder. Also, it'll be really important not to modify any of the function signatures. You can create new functions, you can do implementations of existing functions, but please do not change the function signatures of the functions that are in the code given to you, or you will break the autograder. Okay, so please try it out. You can submit it as many times as you want. Um, Assessment is, I guess, more like validation and not traditional assessment. So you literally get to decide how well you choose to do, right? If you submit it 100 times, you say, I ran the auto grader. I didn't like my score. Let me tinker more with my code. You're welcome to do that. Okay. All right. Any questions? How's it going? People started looking at stuff already? Please make sure to jump on it early. Okay. And as usual, don't hesitate to reach out. Even for the so-called, let me turn this on, so-called naive questions, I implore you, please submit that to the class Slack channel and not direct message. Direct message, you're welcome to send me one if it's something of a personal nature, like your grades or other stuff. But I really implore you to use the class Slack channel. As of last night, the course census is 40, and I'm still just floored at how popular this course is. My experience has been people weren't really that interested in AI, but and it helps me when you post things to the Slack channel. For one, many of your colleagues have the same question, right? But also it helps me to force multiply that others can benefit from that interaction. And somebody dropped a stuffed animal. I don't know if it's yours. Nope. Oh, okay. Oh, it is. Oh, it's attached to your bag. Okay. It's just sort of prominent right there. All right. Any questions? No? Everyone awake? Got a good breakfast? Yeah, awesome. No? Okay. All right, so why don't we jump in? So I'll start out with a question. And this concerns driving, autonomous questions, right? Autonomous driving. And with autonomous driving, of course, the goal is to advance to some destination. Okay. Let me pose the question to you. Is so-called rationality possible with autonomous driving? What are your thoughts? If you could share your thoughts. Rationality. Is it possible? Do we just give up and say no? Elliot? Hmm. 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 Okay, great. So Elliot says that you have different goals, right? And how you do something matters. Any other thoughts? Um, Luke? Luke. See, if you answer, I remember your name, Luke, and I stare at the pictures. Yes, Luke. Hmm. Hmm. Yes, there are rules in place. But let me ask you, Luke, do people always follow the rules? No. I remember my first 2 months working here, I would drive get off the highway to like downtown Worcester, and then I would go up Main South. And I was terrified going about 15 miles an hour because people on side streets would just come out into the main road and they're supposed to stop. People on the sidewalk would just walk out into the street expecting you to stop, daring you to proceed. So, absolutely, the rules are in place, but there's rules and there's practices, right? And in Massachusetts, in Delaware, as a pedestrian, you can get a ticket because you didn't use the roadway the right way. But here in Massachusetts, I was in Delaware for 15 years before coming here. Here in Massachusetts, the pedestrian is always right. Absolutely. Any other thoughts? Yes. And what's your name? Say that again. Amici. Amici. Yes, Amici. Hmm. Yes. So there could be alternative ways of getting to that destination, but each solution, and they're both valid solutions, could have other properties, right? So this idea that Elliot mentioned about different goals, Luke mentioned about rules, and let's sort of extend that statement, constraints, right, on what you can and can't do, and what Amici, right, said, that there are different properties of evaluation associated with particular perfectly valid different solutions. Okay, great, great. So it is possible, but there's sort of like a little asterisk that says, be careful, right? All right. Now, the next question is driving hard? Because you could have your coffee, you're sitting back, listening to your tunes, driving, but that happens, you know, after you've been doing it for a while. So coming to campus now, I know what to expect. But that first 2 months, I was like death grip on the steering wheel. Oh my God, oh my God, oh my God, oh my God. Is driving hard? Is it hard for you? Is it hard? Is it fun? Okay, depending on what fun means, right? Is it hard? What makes driving hard, Jaime? Ah, if we just get rid of all those other people, right? We could just make driving much better. Yes, other people's decisions. Do you have any influence, control, or say over what those other people do? And those other people are also trying to accomplish their goals. And so in some environments, the environment acts back, but in others, it's a little bit more complex. You have other actors, other agents in those environments, and they're also trying to satisfy their goals. Now it's a whole different ball game if, so to speak, if the goals of one another are competing against one another. And that's an interesting issue because you're both trying to maximize some performance measure, and my maximization might mean you are limited in your maximization. And there are frameworks that make that consideration for so-called multi-agent environments. Okay. All right. Any questions? Great. I'm remembering all the names, all right? So it'll take me a little bit to learn 40 names. Well, some of you already know. All right. So let's consider this idea of the architecture of an agent. I forgot I had this. Let's see, turn this on. The architecture of an agent. We'll begin with the environment. Now, we're in the universe somewhere, right? I've seen these pictures of space and it says you are here, right? And in our environment, it's that part of the universe about which we care. For example, right now we care about being in Worcester. Well, maybe not all of Worcester, just this tiny corner of Worcester we call Clark University. And so the environment in which the agent is located pertains to that subset of the universe or that part of the universe about which we care, meaning the state of this environment we care about. So we care about the state of things local to this classroom, but we might not care necessarily at this moment about what's happening in Boston. I don't know what's happening in Boston right now, but it doesn't matter for what our purposes are right here, right now. And so the reason why we care is that what's happening in the environment is going to impact what the agent perceives about things that are going on, because you have to know what's going on in order to be able to act to accomplish this goal we alluded to with the driving example. Moreover, the agent can play actions. It can do things. And when you do things, well, you do things based on what you perceive about the environment. So therefore, the particular environment in which the agent is situated is going to impact ultimately the actions that it plays, the activities in which it engages. Okay. So how does the agent do this? It perceives its environment through its sensory apparatus. More formally, a sensor is some device. It could be a software device, could be a physical device, and this device measures something from the environment. So it's through the sensory apparatus that this agent can devise some representation about what's currently happening in the environment. Okay. Any questions? No? No questions? All right. Moreover, it perceives its environment through its sensors and it acts upon what it sees based on a whole number of things. And we'll unpack that over the course of the semester. All right. And so, what is this thing that it measures? It's called a percept. A percept, more formally, is the content of the environment, and it's measured by the sensors. So most mechanisms, if you think about a mechanism as a robot, a physical mechanism, could be a software bot. The mechanisms put together the state representation of the environment based on the sensory apparatus. And you'll notice oftentimes, especially for real systems in the real world, they have a suite of sensors because there are different aspects of the environment that are relevant to what it is the agent is trying to accomplish. Okay. And so when you measure something from the environment, you're not going to measure it once and then go away. You're going to do it again and again and again and again over the lifespan of the operation of this agent. And that could be a software agent. You can imagine an agent sitting in a data center environment or on a network, and its sensor is measuring the packet flow coming into the router infrastructure across some data center. Now, of course, you're not going to measure it once. There's 1 gigabit per second. No, you're going to measure it again and again and again. And so, in that regard, we don't just have a single percept in time over the operation or the lifespan of this agent situated in the environment, you're going to get a so-called percept sequence. And so it's not just the individual percept that you consider when you're trying to decide what actions to select. You're looking at different properties of the percept sequence. Does that make sense? Any questions? No. So the dual of that is the actuator. And an actuator is a device that projects energy into the environment, allowing action. And that action can be one of very many different things. And there are all sorts of actuators that do all sorts of things. So this particular sensor is a LiDAR. It emits pulses of laser light so many times per second, sits on a turret, and it rotates. And it measures the time of flight of the reflected laser light in order to measure distance in a cone of measurements in the environment around it. And so these devices, those are sensors. These are cameras. The one on the top, you might see in a car that has autonomous driving features. For a lot of these automated taxis, you're going to see something like this, and you'll notice it has a lot more cameras than the suite on top. And when you take pictures from cameras, you'll perform something called object detection. You're measuring certain aspects of the percept sequence that are consistent with pieces of data that you can ascribe labels to, like person, car, bicycle. So you can imagine as this automated taxi is driving around, it's moving, it's constantly measuring percepts, its percept sequence again and again and again and again. And this happens anywhere from 20 to 30 times a second in order to try to put together this notion of the state of the environment in which this agent is situated. Okay. So, oh, and that's a GPS. That was the wrong thing at the wrong time. All right. Um, so let me ask you for these sensors, and I forgot to talk about the GPS. The GPS measures their position, latitude, longitude on the surface of the Earth. And so let me ask you, what aspect of the environment might this suite of sensors together measure? I'll put the question out to you. Any thoughts about that? Why do you need these? What would you use these? What about the environment do you care about? Yes, and what's your name? Chris. Chris, yes. Distance? Distance to what, Chris? Okay. And why is that important? What object? Hmm. Hmm. So you need to know what's out there in the environment. And does what's there in the environment, does it stay fixed? Does it change? It moves around. Do all objects move around? No. Some do. Thank you, Chris. I just want to push on these definitions of environment state. Some move around and some do not move around. Thank you, Chris. And so you'll notice for things like autonomous driving, which is kind of hard to do, you have a set of sensors, not just one type, because there are different aspects of this environment that are important for this particular task. Okay. And so we have also actuators. And these actuators, we said, project energy into the environment, implementing the ability to take actions. And so this is an actuator. In particular, it's a 6 degree of freedom arm. A degree of freedom corresponds to a motor that drives the motion along a particular axis of movement. So there are 6 of them, and then you add a seventh one to move the grippers to pick something up. These are other motors for humanoid. So a humanoid can easily have anywhere from 64 to 100 different motors in it, or degrees of freedom. And together, these motors, if you control them or coordinate them in a quote unquote right way, you can get some very complex set of actions. So an action doesn't just have to be some coarse movement, take one step forward. You can have a very large space of actions. And if you can imagine here with this humanoid, if you had 90 motors or 64 motors, each one of the angular position of the motors, one movement across all those motors represents a different action. And so let me ask you something. If you use your actuators and the agent engages in some action, does the environment change? How does it change? Alexander? Ah, so the agent's position changes. Is that environmental state? Yes, it is, because the agent is part of the environment. So not only are you measuring percepts from your percept sequence in the environment, trying to compute some notion of the state of the environment, you're also part of it. So when you take an action, the environment acts back and results in another state. So there are two factors that are modifying the state of the environment. One of them are the changes the environment evolves through, and that's particularly damning if it's a multi-agent environment. And the other are those state changes attributed to your actions in the environment. Okay. So yeah, all right. The environment is changing. And if you didn't take my IoT class, I'll ask you this question. Are these light emitting diodes? Are those actuators? What do they do? How do they change the environment? What about the environment do they change? Chris? Chris, right? Chris. The light. And so in some application, for example, if you had needed illumination and you had cameras, you would turn on a light and now the state of the environment is changed, right? Absolutely. All right, great. Yeah, I jumped ahead with that. All right. So we have these sensors, these actuators. We have percepts, the content of the environment that you use to calculate the state. And every moment in time, these percepts are being measured or taken, and you have therefore a percept sequence. And so when you produce an action, this action is determined by a number of things. You could consider the current percept. There's a pedestrian right in front of the car, and it's at a certain distance. You need to apply the braking, right? It's the percept that's happening right now. You could also look at the sequence of percepts that this thing has measured over time. Well, you see this little tiny speck in the horizon. You don't know what it is, but it's getting bigger and bigger. And physics says if it's getting bigger and bigger, you must be getting closer and closer. At the same time, your LiDAR is telling you that the distance between you and this thing is getting smaller at a certain rate. So given that percept sequence, the distance is this, it's this, it's this, it's this, you might want to slow down a little bit in anticipation because you're approaching this thing, which at the moment from your cameras is unknown because it's too small. So it's not just what's happening at this moment or snapshot in time. It's also the sequence of percepts over which you can make an evaluation in order to influence the actions that you take. There's also the built-in knowledge. And this built-in knowledge you can think of as an accounting of things that you have encountered in the past. You get these percept sequences over long periods of time, and there are certain pathological patterns that might reoccur. Rather than discovering them each time you encounter them, memorize them in some way, represent them in some data structure. And that data structure could be a traditional data structure, as you would know, or it could be some maybe probabilistic representation. So you have this built-in knowledge, and as you accumulate this built-in knowledge from experience, it helps you to arrive upon a quote unquote good action sooner rather than later. Later, later. So Tesla vehicles, when you're driving it yourself, they're sending out telemetry for various measurements about your steering, what the cameras are seeing, and so forth, because they're collecting lots and lots of data across all of the deployed vehicles about what normal driving looks like. And if you think about it, not just when it's in autonomous mode, but you want to get lots and lots of these percept sequences because that affords you the ability to build up this knowledge. And that's how you improve or get really good in an agent with difficult tasks because you're not just relying on the percept in the moment, evaluations of the percept sequence, you're also building up some type of accounting about prior percept sequences in some form. And so this idea of what makes an agent behave is called its agent function. And as a function, it's a mapping between some percept sequence. Now, and I say that generally, it could be a short percept sequence. Um, the edge case, it could be a single percept in the moment, or it could be the percept sequences and all subsets of that encountered since the agent was first turned on up to the present moment. And so it maps between percept sequence and an action. Now, that mapping can be influenced by many things. It could just be a raw listing. If you see this percept one followed by percept two, do the following. Or it could be some other higher level function or evaluation computed over this. Any questions? No? Y'all quiet, really quiet. Is it because it's 9 o'clock? Or now it's 9:38. All right. So here's an example, and it's a simplified example to illustrate the point about this so-called agent function. Let's imagine this percept sequence consists of two parts. We have the location, and in this grid world, there are two locations we'll call location A on the left and location B on the right. There's also a condition variable that describes whether or not there's dirt in that particular dirt sensed. And so, in an example of a percept is A comma dirty, that means that the robot senses that it is in location A, and it also senses that wherever it is, it's dirty. Okay. So let me ask you, how many different configurations of this world, simplified world, albeit, can you have? Not a trick question. 8. Okay. So we have dirty and not dirty. So for each position, we enumerate and we multiply, right? Okay. Thank you for answering. So we have dirt A, B, so that's two choices. We have dirty and we have not dirty, right? So that's 2 times 2, 4. Simple, right? But is life really this simple? What about driving? You can't do this with driving. So this is an example of a discrete world. A driving is an example of a continuous world. And let's imagine this agent has some actions. It can move to the left, it can move to the right, it can suck the dirt, or it can do nothing. Okay? So let me ask you to fill in this table. If it's in location A and it's clean, what would it do? What should it do? Or what would you do? Luke? No op. Let me see if I can get my pen up and going. No op. How about location A and dirty? Suck, Chris? All right. And I remember a year ago, I bought this new vacuum. It's like a Dyson vacuum. I treated myself, and my brother was asking me, "How's that vacuum?" I said, "It really sucks." So, it's like, yeah, shut up. Um, Anyways, brothers can do that with one of their siblings. What about location B and clean? Um, Colton? No up? What about location being dirty? Nikki? What about A and clean? I don't know why I did that twice. Um, A and clean. Elliot? Why did I do that twice? I think it was just a sequence. All right. Mm-hmm. Mm. Mm-hmm. A and clean and then A and clean. N- I'm sorry? Go right? Okay. And what about A and clean and then A and dirty? So the dirt has returned. They had a dog and the dog tracked mud or something. I don't know. A and clean, then A and dirty. What would you do for that sequence? So the robot was an A, it was clean, and then in the next time instant, the next percept, A and dirty. Chris? Okay. Um, let's just put the suck because it's the percept sequence we're interested in. Okay. All right. Good. You can select an action from a percept or from a percept sequence. All right. So yeah, if it's A and clean, you go right. Okay. If it's A and dirty, suck. If it's B and clean, you go left. If it's B and dirty, suck. If it's A and clean, it's right. Okay. If it's A and clean, A and dirty, suck. Now, in reality, this idea of rationality is an evaluation, quote unquote. Does it act? Does it do the quote unquote right thing at the right times, given the percept sequence? And it's important to distinguish between percept and percept sequence. In some cases, you make an evaluation over the sequence. In other cases, you make an evaluation just at the prevailing percept that you most recently acquired from the environment. Okay? Any questions? No? All right. Excuse me. And so this is a table form that implements a function. It's a mapping between a percept sequence, P star, and an action. But we can certainly implement a function, and there's some pseudocode from the book called the reflex vacuum agent. There's no deliberation happening here. It's just matching percept sequences with actions. But if you, as the designer, craft this function, quote unquote, the right way, you can get behavior that is rational. Now, in this case, the rationality lives in the designer, right? It does not live inside of the agent because it's not doing any deliberation. It's not evaluating different alternatives. It's not encoding any knowledge and recalling, and it's not using skills to build up new capabilities. So there's no learning in place, but it is an honest to goodness rational agent. Okay. So rationality doesn't have to be some big fancy learning system. And in the early versions of the Roomba robot vacuum, it was literally doing something like this quite effectively. Okay. Any questions? No. So let's look more at rationality. You have an agent, you situate it in the environment, and it selects actions according to a percept sequence. I didn't know how to put a figure about any possible subset of percepts, so I just did that. So you select your actions based on percept sequence, which you got a little taste of with this reflex agent. And when you produce these actions, you're causing changes to the environmental state. Now, in the case of the vacuum, when you sucked, well, that changed the environment. The dirt flag was no longer true. When you moved left or right, that changed the environment. Your position was no longer the same. And so, one of the considerations when we design agents for things as complex as the Pac-Man game, the question is, what does desirable mean? You want the environment to converge or to take a trajectory onto some state that is desirable. And so that desirability might be in the end state of the environment. I'm at my destination, or all the dirt is gone, or it could be something about the path that you take in changes to the state for the environment. And so that means you need some sort of evaluative performance measure, some function that will evaluate or examine the sequence of states the environment goes through and give you a score that tells you or encodes something about the quality, the goodness, the desirability of how you converge upon that goal. Does that make sense? Any questions? No questions? No. And so there's no such thing as a mechanical desire or preference. It's either in the mind of the designer, you, or the mind of the user. Some systems, you can customize them. For example, that could be explicit, could be implicit. If you had some vacuum robot, well, simply just the environmental dynamics of the particular home it's in is going to induce certain percept sequences, which will induce certain knowledge structures, which will induce certain behaviors. One of the most pressing problems that iRobot, moment of silence for iRobot, company is no longer, but maybe it'll rise again. But one of the most interesting, and you can search for it on YouTube, maybe I'll post it on the Slack channel. One of the most interesting problems they had to solve with the Roomba robot was dealing with pet waste, right? If your dog poops on the floor, usually they don't. Sometimes they have an accident. Um, Earlier Roombas were taking it and basically finger painting it all over the floor, spreading it out. That's horrific. So they needed to recognize animal waste of different sorts and different forms, and then learn how to navigate around it and not try to attempt to clean it up because you need other equipment for that. So it's an interesting video online about how they did that. They had plastic models, and then they had real uh, scenarios that they set up. So imagine if it were your job at iRobot, testing out algorithms for detecting animal waste. Someone's got to do it, right? Um, but anyways, so read the fine print on those internship jobs, right? No, just joking. Um, all right. So the purpose of these agents, these mechanizations, these machines, is to match the purposes of the designer. In the case of the robot vacuum, does it effectively clean up the space? And there are no two identically same spaces. So the set of actions is going to be different for the same notion of desirability. And it is based or predicated on the assumption that you can correctly specify this notion of an evaluative measure for what quote unquote good performance means. Certainly in the real world, and in some virtual worlds like computer networks, there's a lot of uncertainty. And so in those sort of environments, you have to learn over time. You have to refine based on the percept sequences and changes in percept sequences that you encounter. Any questions? No. And so at any moment in time, and moment in time is important, especially in so-called continuous tasks, you need for rationality a couple of things. You need a performance measure that describes criteria for success. You need some prior knowledge encoded in whatever form that might be. You need actions that can be performed, and those actions could change based on the state of the environment and the agent's configuration in it. And you also need the percept sequence to date. Okay. And so here's an example. We had from before that reflex agent that was just a table, but here is an example of a performance measure. You might want things, excuse me, you might want cleaning coverage to be complete. And so every time you successfully clean a square in a time step, you might reward for that by incrementing some counter, right? And in the early Roombas, it would engage in some behaviors, and its goal was to have coverage. In the newer ones, or the more recent ones, they have cameras, and those cameras are literally building representation for your environment and a so-called map, and then exploring that map for maximum coverage on the floor space, minus the areas of the pet waste. Um, you have to have some notion of the geography of the environment. Now, of course, in some cases, like GPS, that geography is known. You know the roadways are here, you know the junctions are there, and so forth. But in other cases, that environment is unknown, and you have to construct that environment as you move through it. You might also clean squares. Do they remain clean or can they get dirty again? Because that's going to impact your performance measure. You have to know that the vacuum sucking action is actually going to clean the location. You could engage a mechanism in some real examples and it fails to clean effectively. And then you have an action set, in this case, a simplified one, right, left, and suck, and we'll add no op as an action. And then the agent has to have sensors that correctly measure the percept sequence from the environment. So it's going to correctly measure dirt or no dirt. But this is not always the case in practice. And so this idea of performance measure is entirely up to the designer. And at the end of the day, you have to be complete in considering all of those aspects of state, including the action of the agent in the environment, that should be considered in producing this idea of so-called good actions. Okay? All right. And so in this case, our reflex agent, it can be irrational, right? If everything is clean, it'll oscillate left and right. If the vacuum's done its job, it should stop. So that would require you to look at the percept sequence and recognize this fact that it's all clean and then play some action, whether it's auto docking to plug itself back in or to just stop, return to some known position. So while this seemingly is rational, right? And depending on how you think of rationality, do you produce actions that effectively clean the environment? Yes. But this oscillation is a practical problem because in the real world, you'll burn all of your power and now you just have a dead robot that has no battery life in it. Okay. Will the environment get dirty again? Does that mean you have to recheck? Again, that requires evaluation over a percept sequence, not just a single percept. You could have an unknown environmental geography. If you're going to deploy a vacuum robot, well, not every house is the same, right? You might have carpeting. You might have throw rugs that can gum up the mechanisms as it's driving by. So there's all sorts of things about the environment that can confound whether or not the actions are the quote unquote right actions. Does that make sense? Any questions? No? All right. And so each possible person, let me see, ah, there we go. So this is that insect pick and place demo again. And each possible percept is going to select an action that maximizes performance. You have evidence provided in your knowledge base, and you can gather information in order to modify things based on what you might see in the future, effectively short-circuiting this program that selects an action based on the trajectory of percept sequences. You can also adapt behavior. Maybe you have a new percept sequence, new meaning you haven't seen it yet, but it's similar to something you've seen in the past. So you just modify something you did before rather than trying to do that decision making from scratch every single time. And so the learning agent is an important form of our rational agents, and we'll talk about learning agents more so in the second half of the semester when we build the framework for probabilistic methods and reinforcement. And so one of the important things is autonomy. Now, with autonomy, that means you can think of it as unattended operation. So you rely on proper knowledge of the designer, what the designer has encoded, but what makes something autonomous is you're making decisions based on your own percepts. You're not just looking at a program that directs your behaviors. And so an autonomous system is one that makes its decisions from what it perceives, not necessarily some explicit program action. Okay? All right. Any questions? No? And so let's take a look at the type of environments that we can operate in. And when you think about a task environment, there's a type of description that talks about the performance, what you're trying to achieve, and what good solutions look like, the environment, what's going on, the state, how you encode state, the actuators, your ability to behave and do things, and your sensory apparatus, your sensor suite, how you measure percepts in the environment, because that's going to help you calculate some notion of the current state in flight of the environment. And so for the taxi driving problem, you might want it to be safe, fast, legal driving. You might want to maximize profits. Okay, there's always the money side of things, etc. But in your environment, you have other drivers, you have the roads, you have the weather conditions. You'll notice a lot of these autonomous taxis are always in warm environments, like Texas and California, these pilots. The reason for that is snow can sometimes make you think you have an obstacle when you don't, right? It's really hard to drive when it's snowing. Moreover, the road conditions are slick, and that changes what your assumptions are about how the agent moves in the environment. A command to drive might not be the same when it's slick or when it's icy. Moreover, you know that a roadway might have a speed limit of 45 miles an hour, but you're not going to drive 45 miles an hour to minimize the time to arrive on destination if there's snow on the ground. Well, how do you detect if there's snow on the ground? What happens if you're driving and you see some little shiny spot in front of you? So there's a reason why you always see these pilot deployments in environments that are sunny and usually don't have cold winters. Okay. The actuators, of course, there's the steering, the braking, the accelerators, the lights for the traffic signaling, the horn, speech, sensors, cameras, GPS, radar, LiDAR, all sorts of things, and a whole array of cameras. And one of the things you'll notice here with this schematic here of an autonomous taxi is you have some cameras that are high resolution that are used to detect things in the environment, usually forward facing. You have some lower resolution cameras around the sides to look at what obstacles might be around you. You have radar and LiDAR. Radar is good for bearing and speed and direction. LiDAR is really good for detailed distance measurement, much faster than radar can. And so you typically fuse your sensors probabilistically in order to measure state of the environment, particularly where your environment is continually changing, even when you're trying to decide what action to play. Okay? All right. Any questions? No? All right. And so some of the properties that you consider with an environment, one of them is observability. Um, is the state of the environment relevant to the task you're trying to accomplish? Can you see all of it or measure all of it through your sensors, or can you not? So sometimes you have what's called hidden state. And so observability in an environment is going to change the way you implement your agent architecture. You have to analyze the environment and the task. The number of agents you have, is it a single agent or multi-agent? Driving is a multi-agent task. You have other agents operating in the environment, each of which is trying to maximize their performance. And so their maximization of performance might compete against maximization of your agent for its performance. And so that's a really important consideration because that impacts the way you implement your agent function and your agent program. Then there are the state transitions. Is it deterministic or non-deterministic? Is the next state for the determinism uh, version, the next state is determined by the current state and the action. So games like chess are deterministic. Yes, they're multi-agent, but they're deterministic. You know, when I make this move, changing my state, there's a next state that I arrive upon, and that happens every single time repeatedly. With non-deterministic, you're unable to track unobserved aspects of your system. So you treat that as transitions that you can't really model. A number of transitions just occur. So for that, you have to build up knowledge. You have to use things like probabilities. So determinism of state transitions, how they occur, is an important aspect of the analysis of the task environment. Your experience, how you interact in the world, in the environment, gathering these percept sequences. Is it episodic or sequential? And this really answers the question when you interact and you get this percept sequence encoding your experience as you interact in the environment, um, are they self-contained? So you receive a percept and then you perform an action, having memorized or encoded in some way the percept sequences you encountered to date in your knowledge base. If there is no dependence on previous percepts for determining what your next experience will be, that's episodic. The dual of that is sequential, meaning that your short-term action has a long-term consequence. So what you do now when you're driving impacts something that happens 2 steps later, 3 steps later, 5 instances later, an hour later, etc. Then when we look at how the environment dynamics change, rather how the environment state changes, it can be static or it can be dynamic. In the case of static, the environment does not change while you're deliberating. You see your board configuration in chess, you take a look at it, you then think, and then when you go to play your action, you can rely on the board state not having changed. In something like driving, well, while you're trying to decide what's happening, the world is changing. That's a dynamic environment. So with a static environment, you can look at the state, measure the state, effectively close your eyes, make a decision, and play an action, and then evaluate how the state of the environment is different, how it's changed. Dynamic is a little bit different, and you'll find in dynamic environments, you have to make decisions quickly. And in autonomous driving, those decisions are millisecond time scale, right? Which means you have to have enough compute in order to satisfy that deadline. Because if you see some object in front of you, you have to stop now. You can't sit there, close your eyes. Was that a rabbit? Is that a pothole? Is it a speck on my windshield? What am I going to have for lunch today? Oh, and then you hit something, right? You have to make those decisions much faster. Okay. Any questions? No. And so the value of state time perceptions and actions can be discrete or continuous. Discrete means it's countable, and continuous means it's uncountable. And so, how you treat the state, how you represent the state, how you treat the actions is going to be different based on this. Now, we won't do continuous, dynamic types of environments. That's not Pac-Man, but it's certainly multi-agent and there's some uncertainty, some stochasticity wrapped up in it. So then when we look at how the environment changes, it might be known or unknown. If it's known, well, you can kind of model it. If it's unknown, the physics, how the environment reacts as you interact in it, well, you have to learn how it works. You have to make observations. So for example, I have this lacrosse ball, and if I hold it up and I drop it, you can kind of expect you already know where it's going to go over time. If I let it go and it rolls up, you'd be freaked out, right? You're like, oh my God, everyone run. He's a shapeshifter or something like that. So you've learned how physics works, how the environment works, and you're depending on that. If it were unknown, and that happens with infants, and there are a whole host of interesting psychological experiments, they have to learn this idea of naive physics. They have to learn how the state of the environment transitions, and they burn in these pieces of information and recall it, and that helps with future decision making. Okay. And so the hardest task is one that's partially observable. Not all aspects of the environment are viewable. You can't measure them all through your sensors. It's multi-agent. You have other agents that are acting against you, so to speak. Non-deterministic, sequential, dynamic, continuous, and unknown physics. That's the hardest thing. And so sometimes in designing such systems that operate in such environments, sometimes you have to make some engineering modifications to the environment to try to control some things. The consequence is if you're dealing with an environment that's all of these things at the same time, you have to have a very sophisticated sensor suite to measure as much as you can about the environment. You have to have a lot of compute power, represent a lot of knowledge, and recall it. You have to have a sophisticated set of actuators to try to navigate your way through and deal with this environment. Okay. All right. Any questions? No. All right. So let's take a look in the next, we have about 18 minutes left, um, in the next 18 minutes at different agent architectures. And so an agent is an architecture and a program. This idea of an agent function is a conceptual idea that talks about the external view of the behavior of an agent. But how you realize this is with a program. And so you have an architecture, which is your compute device, your sensors, and your actuators. And what an agent is capable of doing is strictly limited by its actuators. A rolling device can't fly. Well, if you roll fast enough and hit a ramp, but it doesn't work out too well. Okay. And so this is a table-driven agent, just like the vacuum that we talked about when you filled in left, right, and suck. An agent program is how you implement this. And this program takes a current percept that is input from the sensory apparatus and returns an action. Now, underneath the covers, it could just be an action by table lookup that looks at the existing prevailing percept, or it could be an agent that maintains some notion of a history of the percept sequence or summary and uses an evaluation on the percept sequence to arrive upon the selection of an action. And so we input our percept, we append it to a list of percepts, and then we look up in a table what action to play. So this is dependent on the designer to decide what is rational. Now, in this, there can be some edge cases, absolutely, that are not modeled. And so as your environment gets more and more complex, this table-driven approach is destined to fail. Going back to the driving example, you can't possibly evaluate every single percept or scenario that can occur in driving. It's impossible. First, it's continuous, and it's an unimaginably large space of things that you can't possibly anticipate. And so, why? Because you can't think of everything. All right. So let's imagine we have big T, the lifetime in arbitrary time steps, lifetime of the agent. And let's imagine we had a table, and that table in the two-dimensional case talks about percept A following percept B, or percept 1 I following percept J. So imagine if the width of this table is the magnitude of the percept set, and the height of this table is also magnitude of the percept set. And let's call this table, let's say this is I, and this is J. And if we have entry I, J in this table, that would refer to percept I followed by percept J. So you can imagine if we had percept sequences of size 2, size 3, size 10, size 100, arbitrary size t, this thing gets very, very big very, very quickly. It's not possible. It's combinatorially just not possible. Moreover, deciding what action to associate with every cell of the table, people don't think that way. We're not very good with combinatorial expansions. And so there are different flavors of agent architectures. For simple task, this reflex agent that we alluded to with the vacuuming example, that works. It's easy to think about because it's a small, relatively self-contained problem. We have model-based. Model-based, you're looking at how the world behaves, a little bit about the physics of the environment. How does this environment change when you do something in it? Now, this model could be something like a ballistic trajectory. When you have some projectile, right, equations of motion physics roughly tells you how this thing is going to move. You can use that with percept sequences in model base to inform and where your system is going and the behavior of your environment. Then you have goal-based, and goal-based looks at what is a desirable end state or end state of the environment. What does success look like? In Pac-Man, it means all the pellets are eaten, and all the food is eaten. All the capsules are eaten, and all the food is eaten. And then utility-based extends goal-based by saying, is this the right sequence? That takes into consideration things like driving. Is it a comfortable ride? Is it fuel efficient? Is it with the least amount of traffic? Is it the shortest distance, etc.? So that utility-based approach, that architecture, talks about not just a desirable end state for the environment, it talks about how you get there. So it looks at the percept sequence as well as that state sequence as you navigate through the environment to achieve some goal. And so here, this is the reflect agent. Not going to spend a lot of time on that. In the reflex agent, you input from your environment, you take your percept, look up in a table, and you play an action from your so-called condition action rules. The condition is the percept sequence, and the action is that particular function you're going to play through your actuators to do something. And so here, you interpret your input, and that interpretation could be something simple, or it could be something complex, like identify the objects in this image, right? In the driving example. Then you look at some rules, okay? And then you play the action associated with that particular rule that you get from your condition action rules. Does that make sense? Any questions? No? All right. So but if you have partial observability in your environment, then you have a serious problem because the percept sequence isn't telling you everything about your environment. For example, I never forget this. I was driving home along Main South, and I saw a gentleman and his daughter. She couldn't have been more than 4 years old, holding his hand, and there was a van parked at the corner of the street. There was a crosswalk in front of me, and I saw the man and his daughter walk obscured or occluded by this van. So there was nobody there, but I said, well, you know what? They're walking. They're probably going to go on that crosswalk, and I can't see them behind the van. So I slowed down to about 5 miles an hour. Lo and behold, he emerges from the other side of the van, just walking by. The van was parked on the corner, and starts to go in the crosswalk. Now, that's partial observability. I didn't see a pedestrian, but just because I saw them disappear behind the van, they could have maybe not taken the crosswalk and just, done something else. But that's a precise example of partial observability problem. So if you are looking up in a table of condition action rule says if there's no pedestrian, continue to move forward, and there would have been an unfortunate collision, right? And I wouldn't be here teaching now. Right? But anyways, then you have the model-based reflex agent. The model part talks about how the world works. I know that something in motion tends to want to continue in motion. So in my mind, I projected forward in time that trajectory of the man and his daughter, even though they disappeared behind the van, partial observability. And so this model-based reflex agent, it still has your condition action rules, but it also looks at how the world changes. And when you play an action, how does that impact the state of the environment? If I'm traveling at a constant velocity, I know that at some time, t plus 1 second, t plus 2 seconds, I know where my position is roughly going to be within some bound of error. So I play that model forward, how the physics works, as well as in the case that I just described to you, I knew they were walking, the man and his daughter, and I played that forward, and they said, you know what? I'm going to collide, right? And so the model-based reflex agent, it keeps track of the unobservable part of the world. And you're using some encoding of physics, both the physics of the agent as well as the physics of the environment. And when I say physics, I mean how the state changes due to each of those influences. You maintain an internal state, and that state depends on the percept sequence. You're encoding the transitions of the environment due to its own transitions, as well as your impact on it through your actions. You're also looking at the percept sequence, right? How you think the percepts might change over time. Absolutely, it could be off somewhat, but it's better than not observing partial observability, those aspects of the environment. So, with all of that, you model what the percept changes could be, the physics of the environment due to those two influences, and you use those in helping you to select the right rule in order to play an action. Does that make sense? Any questions? No? All right. So this is an example, and this is pseudocode. These are all from the book. You input a bunch of different models for the sensors, for the transition of the environment, for the percept sequence. You update your understanding of state, and oftentimes you use probabilities to do this. You get more data. You update your distributions representing these phenomena, and then you select your condition action rule by selecting that representation from the state, and then you play this quote unquote best action. Does that make sense? Any questions? No? All right. So then there's goal-based. This is where we add that criteria that says what is a desirable end state. Now, with this goal state, all right, you have goals. And these goals describe what this best action or what this desirable state looks like. If you have some model and you know how the world works, the world physics, you can play this forward in time and say, is this particular end state or state in time that I have uh, calculated based on my physics, does that match my destination? Is it closer to my destination? Yes, it is. So this would be a good action to take. But this goal-based agent doesn't understand this idea of utility. For example, if you have a four-way intersection, where do you go? Well, you might have more than one solution to the same problem. Okay. Absolutely, the goal can help you define what action you should pursue. And, they work well for many cases, but you might have some competing multiple solutions to a problem. Okay. All right. So that leads to the last one, our so-called utility based agent architecture. You have goals, but what this utility does, it looks at the evolution of the state of the environment as you act as an agent in the environment. And it's asking the question, how happy am I with the way I've done things? And that's things like, is this solution in the driving example, is it fuel efficient? Is it time efficient? Is it safe? Is it comfortable, etc.? And so a goal expresses general good or bad end state. What is desirable? But with utility, you're considering properties of the action sequence. What action sequence has certain values associated with it if you want to humanize it? It's not just that you get to your destination, it's how you get to your destination. Did I have to, really hit the accelerator hard and then hit the brakes hard, right? Or was it a smooth, gentle ride, for example? Okay. And so you can have many different objectives. And when you define a utility function, it's entirely up to you about how you prioritize one of several perhaps competing utility criteria. Okay. All right. So it's important to design a good utility function. If you've taken a commercial flight, you notice when the pilot takes off, when they're going to turn, they always bank the plane before they're turning. That's because they want to create artificial gravity into the floor of the plane because it's not so desirable if they just turn without banking because you're going to be like feeling all of that physics, right? So they've made the decision that smooth ride, gentle ride is a desirable quality because if you didn't like the flight, you're probably not going to fly that airlines again. Okay. All right. And so the last one is a learning agent. With a learning agent, you are evaluating constantly a performance standard, which is a component called the critic. that's giving you feedback to a learning element, and that learning element takes this evaluative feedback, which is continuous, and it issues changes to a performance element, which is what, excuse me, biases the set of actions that you're going to play. And so it says, okay, well, I know that I had a little bit of discomfort with the way that ride was. So instead of using the accelerator the way I did, I'm going to accelerate and decelerate at a slower rate, right? To satisfy this critic, which then says, when I'm in this scenario from my percept sequence, I should drive the following. And so then you have your problem generator, which will propose different sets of actions. And together you arrive upon this idea of acting the right way while compiling in scenarios of when you might play that instead of bootstrapping from scratch all the time. Okay. Any questions? No? So you idea is to build a learning machine and then teach it, rather than trying to uncover all scenarios, all behaviors all the time. And with a learning agent, you can build any type of agent. Trivially true, you can build a reflex agent, you can build a goal based agent, model agent, or utility based with this learning agent. So they're general and they can operate, which is the wonderful part, in initially unknown environments and grow in their competence by assembling a set of skills in their knowledge base. These are sequences of actions that are applied to certain percept sequences, and you use them to build up more complex sets of actions instead of bootstrapping your actions and your tables from scratch. Does that make sense? Any questions? No? All right. So the learning element makes improvements, and I just talked about it. I won't repeat the slide. So you you look at observation sequences of percepts, you look at what your actions do, you build up knowledge of this in some fashion. It could be discrete, usually it's probabilistic, and look at how the world reacts and evaluate that performance, and that continually happens. The nice part is that it allows you to adapt to certain scenarios. I know that there's construction here when there used to not be. I'm going to take a detour because this is going to increase my time and I need to get to work on time so that I can review my slides in the morning and answer emails, right? So you can also adapt to temporary changes in the environment, and those things are partially observable. You can't model those things. Okay, you have to learn them. Any questions? No. All right. So that's all I had for today. We have about 2 minutes left, so I'll end there, and I will see you all tomorrow for lab session.